Now, before I do that, I'd like to talk to you about this man, a man called Professor Thom from Cambridge University. He was an engineer, very well known. He took part in building these bombs, you know, the dam busters in the Second World War. They built these bombs which bounced on the water to destroy the dams in Germany. So he was a very, very sort of intelligent man. He was head of engineering at Cambridge, you know, so quite some person. He also invented the wind tunnel in aviation. All right, so, and he was very interested, he was a Scotsman, he was very interested in the megaliths. And in all his spare time, he would travel around with a theodolite, taking all the measurements. He made plans of over 600 monuments in the British Isles. And he became quite convinced that these builders were using a measurement. And by a statistical method, he put all his, this is before computers, right? He put all his results into this kind of system, and he found that there were these sort of bumps like this, and that they came at regular intervals. This is a pure statistical method, okay? And so he submitted this method to the British Royal Society of Statisticians, who did a two-day thing on this and decided that Professor Thom's method was perfectly acceptable, and that the distance that he had found, the measurement he had found, could be seen to exist without any doubt. He called it the megalithic yard, and its result was 0.8294 meters. This is the result that he came to after his work here in Karnak, because he actually did all the measurements here in the Karnak alignments, and he came up with this result, 2.7211 feet. And he also discovered that this yard was used in units of 2.5, which he called the megalithic rod. It was equal to 2.5 megalithic yards, which was 2.0735 meters, or 6.8028 feet, okay? So this is the measurement that Professor Thom found. Now let's look at the size. If this megalithic rod of 20735 meters was used as a measurement here on this rectangle, if you take the diameter, we said, of 42.38 units, that gives you a measurement of 87.87, which is 288.3 feet. This is the exact measurement of the Aubrey circle given by Petrie. So, in other words, there's the Aubrey holes around the circle, and there's the distance, 288.34 feet, going across the Aubrey. Here are the Aubrey holes. These are the two station stones, and that's the distance across the circle. Okay, so on Google Earth, we can measure it as well, 288.34 feet. Okay, so in other words, if this system was used, the measurements were 7 megalithic rods by 20 megalithic rods. Okay? So we actually see that we have a measurement which has been, you know, accepted as a perfect measurement for the megalithic builders, which was used 7 by 20, and the diameter is exactly the diameter of that. So this would quite clearly indicate that the rectangle used to trace the holes was 7 megalithic rods wide by 20 megalithic rods long, and it confirms the tracing method of the use of the megalithic rod in 3000 BC. I hope you followed that. It's not too complicated, but it's quite important because, in fact, this is unknown. No one has ever realized this before. And so we can quite clearly see that these builders were using exact measurements and sophisticated geometry. So now the next question is why? Why divide a circle into 56? Because we've been talking about 60 for the others. Why is 56 here? Now, if you remember your multiplication tables from school. 8 times 7 is equal to 56, which means that if you have 56 holes around the circle, you can divide that circle either into 8 or into 7. Okay? If you divide it, you can have 14 gaps per quarter. Okay, if you divide it into 4, and if you divide it again into 8, then you have 7 gaps per quarter. A quarter of a circle is 45 degrees. Okay? So you're dividing your circle into 7 gaps of 45 degrees. At 45 degrees, you're dividing into 7 gaps. Now, that's very interesting, because we know that that's what the Egyptians did. We have written evidence of this. The Egyptians had a thing called the seked, which meant the slope. And between the vertical, they put a cubit on the vertical plane and the horizontal plane. So that if you have 1 here and 1 here, that makes 45 degrees. And then they divided the base into 7. And so the slope was decided as to where you would put it. Each segment was called a palm. And each palm could be divided into 4 to make 28 altogether. So the idea of taking 45 degrees and dividing it into 7 parts is exactly what we find in Egypt. We have written evidence of that. And so finding it here in Stonehenge is very interesting. 45 degrees divided also into 7 parts, except that here it's divided on a horizontal plane. In Egypt it was vertical. And because it's placed on the arc of a circle, then these are equal angles. Whereas in Egypt, they would change slightly. 56 is also 7 times 8. It was 8 times 7. Now it's 7 times 8, which means you can put a 7-pointed star in there. You can divide the circle into 7, and this time you'll have 8 gaps between the points of your star. Now, dividing a circle into 7 is very interesting. 360 divided by 7 gives this number, 51.428571. Now, that described as a latitude is the exact latitude of the center of the Avebury circle. I don't know if you know of Avebury. It's a big stone circle north of Stonehenge. Its exact center is exactly on the latitude 51.428571. So it is exactly 1/7 of the distance between the North Pole and the equator. No, the North Pole and all the way around. It's 1/7 of the way along the Earth's meridian. That's it. So if I put the Earth on here, inside the Stonehenge circle, there you go, well, Avebury is here. Okay? But it doesn't stop there, in fact, because if you can divide it into 14, you can divide it also into 28, so we can divide the circle into 28 sectors. And this will give us different latitudes on which we're going to find the most important sacred sites of history. So you have the equator to start off with. So 1/28 of 360 gives you 12.857142 degrees. If you multiply that by 2, you come to Karnak in Egypt, which is at 25.714285. Then Delphi, where the oracle was in Greece, at this latitude. But also, you also have Évora in Portugal, where there are enormous megalithic monuments. And these monuments in Évora in Portugal were built at the same time as the monuments here in Karnak. They are very old, 4,700 BC. Very, very impressive monuments at Évora. And the cathedral at Évora, the Évora Cathedral, is exactly at this latitude. Exactly. You know, this is precise to like 1 meter. the Evora Cathedral is exactly on that latitude. And then you have Avebury, which we've seen is another, if you add this again onto that, then you get this. So the division of the circle into 7 seems to have been something that the ancients were very interested in. Now, I said earlier that there was a particular thing about the choice of the latitude of Stonehenge. At the latitude at Stonehenge, it's the only latitude where you get an exact right angle between the sun solstice and the major moon angle. So I've got all the angles. This is a map by a plan made by a man called John North, and you have the 4 station stones around the edges here. These 4 points are the 4 station stones. So these are the angles of solstice and major moon. And you can see that if you add the solstice angle to the major moon angle, you get exactly 90 degrees. Although these angles, you see the year, it's minus 2980. That's when you get exactly these results. So it's 5,000 years ago, almost exactly 5,000 years ago. Because we're in 220, it'll be 5,000 years ago. And if you add these together, you get exactly 90 degrees. So if you put a square orientated correctly, then you're going to be getting a right angle. And what you can see here, you see, is that on these station stones, one side, the short side, is pointing towards summer solstice sunrise, and the long side, sorry, where are we? The long side is pointing, well, it's off the screen, I think. The long side is pointing towards the major moon. So here we are, this is a diagram. This points towards solstice sunrise on the first day of summer, Midsummer's Day, and this points towards the major moon rise every 18.6 years. There you go, summer solstice. And then the moon, major moon south. So they're at right angles to each other. And this rectangle shown here, with its right angles, actually points to that. There's a right angle there, you see. Now, you've heard of Pythagoras, Pythagorean triangles, the right-angled triangles with whole numbers around, like the 3, 4, 5. This is used to make a good right angle in a building. You measure 3 feet one way, 4 feet the other way, and when you have exactly 5 feet between the two ends, then you've got a perfect right angle. That's why, you know, if you want to build square buildings, which is useful for putting your furniture in the corners, then you use the 3, 4, 5 triangle to do that. And this is another one, the 5, 12, 13. These are whole numbers on all 3 sides. Whereas on a lot of other triangles, you know, if you have, say, 1 here and 2, 1, 2, then you're going to have a square root on this diagonal, which is a kind of irrational number. You don't know how much it is, really. Whereas the Pythagoras triangles give you whole number results, which is very useful. Okay. Now, Pythagoras lived in Greece at about 500 BC, so this is 2,500 years before that. And these guys were using these things already, because if you add these angles together, the station stone, you see that, in fact, with respect to the angle of a Pythagorean triangle, a 5, 12, 13, it's built with a precision of 0.055 degrees. In other words, 5/10 of a degree precision for an exact 5, 12, 13 triangle. So those 4 stones, which were placed on the circle, have been positioned in such a way that they create a triangle of Pythagoras with whole numbers, giving a value, of course, because if you have 5 on this side and 12 on this side, then you have 13 across. So you have a whole number for your diameter. And those 4 stones show that geometry, but they also show summer solstice sunrise and the moonrise. So this only works at this latitude, at that particular time. Okay? So there's very high science going on here, linked to the heavens and the earth. All this is linking the heavens and the earth, which is the aim of any sacred site, really. I've put here that there are 2 centers. I'll come back on that just in a second, because, in fact, there are 2 different centers at Stonehenge. Now, let's look at the diagonals, because if you have this rectangle, then it has 2 diagonals. Okay? And I'm very interested in diagonals, because all my work here in Karnak has shown that these people were very interested in diagonals. They used the diagonals as a sort of basis for their architecture. And I've seen it to be the case elsewhere. For example, there's a thing in called, in Iraq now, called the ziggurat at Well, this is not a known fact, but the diagonal, it's a rectangular shape. The diagonal of that is exactly north-south. Okay, so that monument was placed according to cardinal directions along its diagonal. And once you learn the key of the diagonal, then you look at things in a totally different way, and you see how everything just suddenly jumps out at you. You suddenly understand a whole load of things. So I get very interested in the diagonals of these things. And so the diagonal of the station stones, in other words, a line which goes from one station stone to the station stone in the opposite corner, right? I get interested in that. So when I trace that diagonal, I'll spare you all the number crunching here, because these are all sort of angles and things just to show that, you know, it's actually worked. And then you get an angle here of 26.76 degrees north of west. Now that is very close to the angle of a double square. Double square is 2 squares placed side by side, and they're diagonal. And what I discovered is that if I place the exact angle here of a 5, 12, 13 triangle, so I go from the principle that this is an exact 5, 12, 13 triangle placed here, then this diagonal here, there you see is the rectangle, the 5, 12, 13 with its diagonal. The red line is the diagonal of a double square placed exactly on the cardinal directions. So if you're wondering how these people positioned this 5, 12, 13 rectangle so that it would aim at the moonrise and the summer solstice sunset, this is how they did it, by placing simply a double square, in other words, a thing which is twice as long as it is wide. It's the shape of the king's chamber in the Great Pyramid. It's a double square on the base, you know. It was used a lot, the double square. It's also the temple of Solomon. Solomon's temple is a double square. It was used a lot in sacred sites. Well, this is a double square placed on cardinal directions, and its diagonal is also the diagonal of the 5, 12, 13 rectangle used to position the sun and the moon. So now we're beginning to see that there's another geometry here behind this sun and moon angle. This all starts getting very strange. So the exact angle, the angle given here is 49.23 degrees. If we do it geometrically, the exact angle is 49.185 degrees, which is a difference of the given angle of 0.05, 0.045. In other words, it's very, very close to the actual angle which has been taken on the site. All right? again, 5/100ths of a degree. So here we go. That's the first diagonal. But again, so this enables us to say then that the major moon angle at Stonehenge is the sum of the angles of a double square and a 5, 12, 13 triangle. If you take those two angles, you add them together, you get the exact angle of the moon angle at Stonehenge. Okay? Now there's another diagonal, the diagonal that goes from the other square up to the top here, and that is a triple square based on the cardinal directions. Okay? So you have 1, 2, 3 squares oriented north, south, and that gives you the other diagonal. All right? So double square, triple square, and the 5, 12, 13 goes between them. Can you see that all this was done with 4 stones?
Very efficient.
Incredibly efficient.
Yeah.
In conclusion, it's not quite the end. I've just got a little thing to say, but in conclusion to all this geometrical thing, it's just a repeating what I've already said. The 5, 12, 13 Pythagorean triangle was used in England 5,000 years ago. Its diagonal was placed over the diagonal of a double square orientated on cardinal directions. This indicated the major moonrise at a specific astrogeometrical characteristic of this latitude, a right angle between the sun solstice and major moon angles. Okay, that's all of that in a sort of one-sentence nutshell. I thought I'd point out as well that Atkinson, who was a very well-renowned archaeologist and did a lot of work on Stonehenge, gave the short length of the station stone rectangle as to be a distance of 33.3 meters, which is exactly 1/3 of 100 meters. So, as you know, often a yard is divided into 3 feet. So if you divide a meter into 3 units, like you have a metric foot, well, that distance would be 100 metric feet. Because it's 1/3 of 100 meters, it could be called 100 metric feet. So again, we've got the meter showing its face here.